Vivian wants us to be safe and our code on the web to behave. Use Rust to generate code that will validate risky inputs. No need to be brave.
Hello, my name is Vivian Band and I'm a second year PhD student at the University of Glasgow studying network security. I was an intern on the Improving Protocol Standards project, which is still ongoing and is led by Colin Perkins with Stephen McQuiston and Deges Jacob as research assistants. So, Improving Protocol Standards. The Internet Engineering Task Force standardises network protocols. These are initially presented as drafts to working groups and then become official standards after further review. However, even after all of this peer review from several different sources, mistakes still sometimes appear in these standards documents. For example, in the image on the right, the ASCII diagram claims that the field option relay port is 13 bits long and option len is 19 bits long, but the text description says that they should both be 16 bits in length. These errors and inconsistencies create ambiguity for people implementing protocols. What the Improving Protocol Standards project aims to do is create a machine-readable ASCII diagram and text description format to allow us to detect these inconsistencies much more easily. These are minimally different from the format used in existing diagrams and descriptions, with authors needing to use consistent label names and certain specific stock phrases in their descriptions. These machine-readable documents allow us to build a typed model of protocol data. We call this custom type system, developed as part of our project, Network Packet Representation. Network packet representation is programming language agnostic, so we can use it to generate outputs in any language that we like. I had used Rust earlier to implement a bare bones version of the Quick protocol a few years ago as part of my final year undergrad project, and I was impressed at how much safety it added to systems programming. So, Rust was my language of choice for this internship project. Our first automatically generated parser libraries would be Rust files because we wanted our resulting parsers to provide a good level of type safety. Okay, so first of all, let's take a step back and take a look at which types we need to describe network protocols. Before we can start building parsers and parser combinators, we need to know which basic types we'll need to parse in the first place. This internship was my first experience with parsers. I use a lot of analogies when I'm trying to learn new concepts, so I like to think of these basic types as Lego bricks, which we can use to build cool, more ambitious structures later on. There are several basic types that we can identify from protocol standards documents, so we'll take a look at a TCP header as an example to demonstrate this. Fields which contain raw data can be modelled as a bit string, so source port is just a 16-bit unsigned integer, that's just raw data. Fields which could contain one or more of the same element could be modelled as an array. Some fields only appear under certain conditions and rely on values from other fields within the same protocol data unit, in this case the TCP header, to establish whether we're using that or not. So we can call these constraint types since they need to be checked. Some fields require information not contained within this packet, like an encryption key or a value from another protocol data unit somewhere within this draft. We can hold this information in a context data type, which can be accessed by other protocol data units, which also feature in this draft when required. A field which can take on one of a limited possible set of values can be modelled as an enum. So we've got them here. An enum is indicated in these drafts with the stock phrase, a TCP option is one of. So is one of is the key phrasing we would need to use in these modified standards documents. Packets and protocol data units as a whole can be considered as structure-like types, given that they contain a sequence of field types as constituent members. One data type which doesn't feature in TCP but is integral to Quick would be the function data type. So these are required to perform conversions between different protocol data units. In this case, it would be encryption and decryption of Quick's protected packet headers. So we've got 7 types in total in our network packet representation system. Bit strings, arrays, structs, constraints, contexts, enums, and functions. So now we get to the fun stuff. Automatic Rust parser generation. So we've got our basic building blocks sorted out. Now how exactly can we use them to build more complex parser combinators in Rust? So let's use that bit string example that we went over in the previous section when we were explaining our custom types. We can automatically generate this custom Rust type as a wrapper around an unsigned 16-bit integer in our Rust output file pretty easily. Immediately after that, we can generate a nom-based parser for that type. So this is a little bit more difficult to generate. There's a lot going on here, so we'll highlight a few key details. Our first argument for all of our parser functions is an input tuple. The first element of this tuple is a borrowed array of bytes, which for protocol testing would be an incoming packet of some sort. Our parsers work at the bit level, so the second tuple element is an integer which tracks how many bits we've read in the current byte. Our second argument is a mutable borrow of our current protocol's context instance, since we might want to update this as well as read from it. Our outputs are a nom-specific result type, containing the remaining bytes left to be parsed, an updated bit counter, and a TCP header item instantiated with the correct value read from the byte array. We also return a mutable reference to our possibly updated context. The parser function itself takes a defined number of bits from the input byte array, in this case it will take 16 bits, and then assigns the value of those taken bits to the custom Rust type as needed. The order in which we generate these custom types and parsers in the Rust output file is determined by a depth-first search. We generate a custom type and parser whenever we reach a leaf node, and then generate the parser combinator for the parent nodes when there are no more leaf nodes found for that parent. So let's walk through parsing a TCP header. The overall protocol data unit is a TCP header, which is a struct type in our custom network packet representation system. So this is the root of the depth-first search tree, and we'll generate the parser combinator for this last, after we've generated all of the required dependent parsers and parser combinators. So the first parser will be for source port. This is a 16-bit long bit string, and was the parser that we walked through earlier. Bit strings are leaf nodes, so we move on to the next child of the root TCP header node, destination port. This is also a bit string, and therefore a leaf node, so we write a custom type in a 16-bit parser for this. The first non-bit string we encounter in TCP header is options, which is an array type. The elements which could be present in the options array are TCP options. TCP options is an enum type with a limited range of possible choices. Each of these enum variants are described in their own small ASCII diagrams in another section of the same document. This makes each enum variant a struct type in our network packet representation typing system. In this case, EOL option is a struct. The value of the field in this ASCII diagram is a bit string. This means we've finally reached the leaf node, and we can write a custom Rust type definition and a nom parser for EOL option kind, and then a Rust type definition and a parser for its parent node, EOL option. We find that there are more TCP option variants, so we repeat this process for each one. Once we have written parsers for all of the variants, we can write the Rust type definition and parser combinator for the parent nodes, TCP option, and then options. The last field in this packet is the payload, which we can process relatively easily as a bit string. Finally, we write the Rust type definition for the TCP header struct, and the parser combinator to process the entire protocol data unit in one function call. We also create a context object, which all parser functions have access to. So, to recap the system that was developed in this project, we have the machine-readable protocol document in stage 1, with our minimal changes to ASCII diagrams and text descriptions. We have the custom protocol typing system developed in stage 2, our network packet representation language. In stage 3, we have the results of my internship work, a Rust library file containing correct, usable parser functions automatically generated from the information we have in stage 2. Remember earlier when I mentioned that I think of these basic types and parsers as building blocks? To go further with that analogy, a TCP header is a lot like this Lego block dinosaur here. It contains many different complex elements, and it's difficult to build manually without making mistakes. Our generated parser libraries are not only a manual explaining how this data should be parsed, they also allow protocol developers to build the struct with extracted values with a single function call. This is ideal for protocol testing. The picture on the left is a genuine sample of our generated TCP parser code from our modified TCP RFC document. So, conclusions. Initially, I decided on Rust as our first parser output language because I enjoyed using Rust for systems programming on a previous project. Using parser combinators in NOM turned out to be an ideal fit for parsing protocol data, since parser combinators and assigning types to network protocols both use depth-first search. Parsers can be difficult to write manually and are prone to containing errors. Automatically generating parsers minimizes the chances of some of these errors occurring. For example, the number of bits being read will always match the specification. The typing guarantees offered by Rust helps us to be sure that we're using the correct types in both the machine-readable protocol specification document and in our network packet representation system. If there are errors, the Rust compiler will alert us to this. Next steps. This project is still ongoing, and there are more directions that this research could go in. We're aiming to introduce our system to the IETF to see how this system works in practice with helping with protocol development. We need to put in more work on function types so that we can create things like encryption and decryption functions for protocols like QUIC, which heavily rely on this. We'd also like to use these generated Rust parser libraries for automated protocol testing and error correction, and to support more output languages in the future. Resources for this project can be found at these links. We have a peer-reviewed publication which goes into more detail about our network packet representation typing system, and a GitHub repository containing the code for our automatic Rust parser generator. Thank you for your time, and I'd be happy to answer any questions. That was brilliant. Right. Loved it. Thank you so much.
Thank you. So I know we have like a 25 to 30-second delay to the stream. So just to get ahead of time, I have 2 questions, if you don't mind. So the first one is, there's a push for native implementations of the networking type. So the Rust standard library doesn't use libc anymore, but directly operates with system calls. Do you think that will affect you in any way, or like in developing new types?
Potentially. I mean, so the whole point of us developing the network packet representation system was to have something that was completely agnostic of any programming languages or output libraries we want to use in the actual parser files themselves. So it should be fairly easy for us to adapt to these things, I would think.
Cool.
Like, I think we could maybe we might have to consider like how we would convert from network packet representation to different codes featured in the different types, featured in the output code files. But that's relatively straightforward, I think.
Wonderful. So this feeds into my other question. So I guess you can use the higher level parsers for, let's say, TCP, UDP, whatnot, regardless of the underlying types of like IPv4 versus version 6.
Yes. So what we're aiming to do is have these run through a single protocol specified in a draft. You know, it's very rare that you would have an RFC that specifies multiple protocols. So if you wanted to make an IPv6 generator, sure, go ahead, run it on that RFC. So what we're aiming to do is introduce our machine-readable ASCII format to future IETF drafts, and hopefully we'll see more adoption of that so we can have automated testing going forwards. But what we've done for showing the TCP example, we've gone through an old RFC and made minimal changes to it to allow us to generate parsers. So if you want to do that with old protocols, yep, that's totally fine as well.
Cool.
So I guess in answer to your question, sorry, the question was about multiple protocols, sort of nested, wasn't
it? If you can use the parser that's coming out of the RFC for TCP, you can use that for v4 and v6 and netlink and what else there is.
Yeah, we can use this for all sorts of different protocols. I think the nice thing about parser combinators is if you want to get really ambitious and say, okay, we've got an IPv6 packet containing a TCP packet, you know, you can have a parser combinator that does that, if you like.
Oh, yeah.
Maybe one day in the future.
That's a thing.
Yeah.
Cool. Wonderful. There's also a question from the audience. How do you deal with non-byte aligned structures? So if like a 5-bit word crosses the 8-bit alignment.
So I think I had a small file for testing when I was doing the internship about, okay, what if this happens? And non-byte aligned words was one of them. So what we found was with the bit level parsers, it tends to just go straight into the next byte. if you happen to the count to exceed 7. So it will just run forwards, quite happily. We haven't found any issues with that so far. Nom has been very good to us.
Yeah.
Yeah.
Oh yeah, it has been released, right? Version 6 has been out since Tuesday, I think.
Yeah, so unsurprisingly, haven't had time to update that yet. So ours is written in Nom 5, but yeah, we'll see if it still works with 6 and if there's anything that we need to change.
Yeah, wonderful. If this were a physical conference, we would probably meet Jeffrey, who wrote the thing.
Sure. Yeah, we'd love to.
Wonderful. Do you want to precise something or say, hey, this is like something that came to mind just now?
No, I think I've kind of said everything that I want to say in the presentation, mostly. So it's mostly a proof of concept at the moment. So I've posted a link to the repository and our paper explaining our system in the conference room chat. So if people want to take a look at our library, have a play about with it, see how the generated Rust codes looks, we would happily take feedback if people want to help us improve our parsers. So I would consider myself still quite a novice at Rust. So we wrote everything using nom functions as opposed to the macros, so we could sort of expose how much was going on, just so we could make it clear to ourselves. So if people want to talk to us about how we can optimize that or make it a bit cleaner, more improvements, that would be great. We'd love that.
Cool. Wonderful. So, to the lovely people in the stream, this is about the last chance you get to ask more questions. HS Vision has one. Has the ITF been receptive to the machine-readable diagram format?
So the problem with the ITF is there's so many different groups. It's impossible to get like a group consensus for the whole organization. So what we've got at the moment is a small side meeting. The formal descriptions and techniques side group, I think, which is aiming to sort of like see, okay, how can we deploy this? But we have, so Stephen McQuiston and Colin Perkins, 2 people involved in this project, are heavily involved with the IETF. So I think they're having discussions to see how we can get this more widely deployed. So there's been past attempts about like, okay, we can have custom tooling to do this, this, and this, and it's all singing, all dancing. But what we tried to do was make something relatively simple and unintrusive that could work with multiple workflows. So that's why we're hoping this will see wider adoption.
Cool.
So the answer is we don't have anything published using it yet, but watch this space.
I guess you will be trying to investigate like the correctness of the middle boxes and whatnot, or maybe try to circumvent them. Cool.
Yeah, so one of the examples that we're working on at the moment is Quick, with Quick being very high profile and a very complex protocol. So we think if we can successfully parse this and, we can successfully use it for testing, then we think that's quite a good promotion, I suppose.
Definitely.
Yeah.
I mean, having an actually correct implementation that's like done when the specification is finished.
Well, this is the other problem. This was one of the main motivations about, like, you've got protocols that are becoming increasingly more complex, like Quick. It's not surprising that there will be stuff, there will be flaws in it. So say if we got a packet generated by a C-based implementation of Quick and we fed it through our Rust parsers, we could, potentially find errors that way. So it's interoperable with stacks written in other languages. We just need the sort of output that they generate.
So with tools like Cargo, Expand, I could then see at the generated code and maybe check out the state machine that has been generated to see if like the specified behavior makes any sense, right? Or if there's like obvious flaws in the standard that you cannot see by just reading the text.
Yeah, that's the aim, to sort of catch the subtle bugs, where it's like, okay, essentially what our parsers are testing is your output on the wire correct? Is it doing what you think it's doing? We can maybe come up with sort of like more advanced testing harnesses and sort of automated error correction and things for stacks later on, possibly, but that's going to take some time to develop.
Yeah.
Ooh.
Looks like a long ongoing project with very much potential.
Hopefully, yeah.
Wonderful.
Cool.
So I'm currently not seeing any more questions. I hope I haven't missed any.
Nope, seems like that's all of them.
Wonderful. Then thank you again very much.
Thank you for having me.
Yeah, you're welcome.